Dear students, today let us find out self-inductance of a solenoid. Now, what we do is, we consider a solenoid of length L. Now, let small n be the number of turns per unit length. That means small n is equal to capital N by L. Here, capital N is equal to small n into L. That is, here capital N is the total number of turns on the solenoid. Now, what is a magnetic field inside the solenoid? When you pass a current, you have a magnetic field created inside the solenoid. Now, this magnetic field is uniform and it is given by B is equal to mu naught Ni. Now here B equals to mu naught Ni. Here mu naught is the constant or permeability of free space. Small m is the number of turns per unit length, and I is the current. Now you see, B is directly proportional to N. In other words, when you have more number of turns, then magnetic field is also large. When you have more current, that means if you pass a large current, then magnetic field is also large. So this is the expression for magnetic field inside the solenoid, and this field is uniform. Now we can deduce it also in other chapters, in other classes. We will show the deduction of this. Now let us find out self-inductance of a solenoid. Now how to find out? Now when a current passes through the solenoid, then flux is linked with it. Now how much is the flux phi? The flux phi is equal to, we know, B into A. Now what is A? A is the area of cross section of each of the coil. Or you can write flux phi is equal to B. B is how much? B is mu naught Ni into A. So this is the flux linked. This is the flux linked with each turn of the coil. Now, what is the flux for the entire coil? Mu naught Ni into A into NL. So, if you multiply it by NL, this will be the flux for all the turns. This is the flux for one turn of the coil, and if you multiply it by NL, then this is the flux for all the turns of the coil. So we can write from here that flux phi is equal to mu naught Ia into N squared L. This is equation number 1. This is the flux for all the turns of the coil. Now we have learned in the earlier classes. That phi is equal to L into I, where L is known as the coefficient of self-induction. So we can write I is equal to Li is equal to this phi. So we can write Li is equal to how much? Mu naught Ia N squared L. So from these two equations, we get L is equal to how much? Mu naught Ia N squared L divided by I. So this I gets cancelled. So L equals to how much? Mu naught A into how much is N squared? N squared is capital N squared divided by L squared into L. So L is equal to how much? Mu naught A into capital N squared divided by L. So this is the expression for self-inductance of a solenoid. So here self-inductance L depends upon A, the area of cross section of the coil. So large area of cross section, more the self-inductance. N, that means the N is the total number of coils, if you have more number of coils, then self-inductance is also large. And largely, length, L is the length of the coil. So larger the length, less the self-inductance. So this is the expression for self-inductance of a solenoid. Now let us see how to find out self-inductance of combination of coils. Self-induction of combination of coils. Now there are two combinations possible. One combination is a series combination, another combination is a parallel combination. Now in a series combination, there are two inductors of inductance L1 and L2. These two inductor or the coil is connected between 2 points A and B. Now let E1 and E2, this is first we are doing coil in series. Now let E1 and E2 be the potential difference across these two coils, across L1 and across L2. So the total potential difference E equals to E1 plus E2. You can write like this. But we know that induced EMF E is equal to minus of L into di by dt. So we can write here like this, that minus of L into di by dt is equal to E1 plus E2. So if for E1 and E2, we can write it as minus of L1 di by dt plus minus of, again this plus and this minus, so this minus here, so this will be L2 into di by dt. So you can write like this. What is L? L is the inductance, total net inductance of the two coils. What is L1? L1 is the inductor of the first coil, L2 is the inductor for the second coil. So we can write from here that minus of L is equal to minus of L1 minus of L2. Or we can write L is equals to L1 plus L2. So the net inductance of two coils is L1 plus L2. So this is similar, just like resistance in series. Remember resistance in series? For resistance in series, we have net resistance or effective resistance is equals to R1 plus R2 when they were connected in series. So just like that, inductor L equals to L1 plus L2. Now let us find out for the parallel combination. Now in the parallel combination, so number two for the parallel combination. Now for the parallel combination, you see the current I is divided into two parts, I1 and I2, and then they get combined to form current I again. So these are the two inductors having inductance L1 and L2. So we can write the total current I equals to how much? I1 plus I2. We can write like this. But we also know that induced EMF E, this is equation number 1 set. So we know induced EMF equals to how much? Minus of L into di by dt. So what we have to do is we differentiate this equation number 1. So if differentiate equation number 1, it looks like this: the di by dt is equal to di1 by dt plus di2 by dt. So it looks like this. So what we have is induced EMF E is equal to, let's write it again, it is minus of L into di by dt. So how much is di by dt then? Di by dt is equal to minus of E divided by L. So di by dt is equal to minus of this minus in here, down there, so it is minus of E by L. Now let us write this as equation number 2. So if you substitute di by dt as minus of E by L, it looks like this. The first one is E by L. It looks like this. and this is di1 by dt. So the second equation will look like this. This is minus of E divided by L1. For the second equation it looks like this, minus of E divided by L2. So if you take the all E outside cancels both sides. So you can write 1 by L is equals to 1 by L1 plus 1 by L2. So you can write it like this. So you see, this is the effective inductance of two inductors, L1 and L2. So 1 by L1 plus 1 by L2 is equal to 1 by L. Now this is similar like resistance in parallel. For resistance in parallel, remember we have to write the effective resistance 1 by R equals how much? 1 by R1 plus 1 by R2. This was the effective resistance when resistance were in parallel. So similar for case of inductor. The effective inductance is 1 by L is equals to 1 by L1 plus 1 by L2 when they are connected in parallel. So that's all about self-inductance of combination of coils. Thank you.